Assalamualaikum and hello everyone. Today our team will be presenting to you about our solar farming station designed to maximize the energy harvested by each solar panels. It is not only saving the energy but also eco-friendly. So in this presentation we will cover about the importance of rotating solar panel, and also we explain in more detail about our solar farming design station. Alright, so without further ado, let's go.
I'm going to explain about the importance of rotating solar panel for green energy. So the first one is optimizing the absorption of solar energy. So why it matters? It matters because the sun move across the sky from east to west, meaning that fixed panels only receive optimal sunlight for a limited time. And then the second one is because rotating solar panel, which is a tracking system, adjusts their position to follow the sun's path to ensure continuous exposure. So the second point is reducing angle mismatch related energy losses. So I give an example. The example is a comparison of rotating and fixed panels side by side with the spinning panel, getting more direct sunshine. So why it is important? It is important because solar panels are more efficient when the sunlight hits them perpendicularly, which is 90-degree angle, and then rotating panels ensure optimal positioning, reducing losses and maximizing electricity generation. Third one is enhancing the production of energy in different seasons. The example is panels angles are changed between summer and winter settings via a solar tracker. It is because the sun's altitude changes throughout the year, which is in summer, the sun is higher in the sky, and in winter, the sun is higher in the sky. And then fixed panels are optimized for only one season, leading to lower efficiency in others. The last one is improved efficiency in cloudy environments. The example is smart tracking panels on a solar farm can adjust to low light levels. Why it is important? It is because on cloudy or overcast days, sunlight is scattered rather than direct. And then the second is fixed panels remain in one position, capturing less diffuse light.
I will be presenting the design of the solar farming station. So there are two components to consider in this design, which are the sun rays and the solar panel's normal. We have vector S as the sun ray vector and vector N as the normal of the solar panel. The solar panel's normal is perpendicular to the terrain where the solar panel is placed, like in the picture. Since both the Earth and the Sun are spheres, we have to represent them in a 3D space. Hence, we consider the directions of X, Y, and Z. Alpha is the Sun's elevation angle from the Earth to the Sun, and beta is the solar panel's tilt angle from the terrain. Gamma and phi are the azimuth angles of the Sun and the solar panels respectively, which are the horizontal direction from north to south on the terrain. Hence, shown on the screen is the formula on how to get these vectors. So we have Sx cos alpha times sin gamma, Sy cos alpha times cos gamma, Sz as sin alpha. And for the solar panel normal, we have Nx, which is sin beta times sin phi, Ny, sin beta times cos phi, and Nz cos beta. With both of these vectors considered, we can design a proper solar farming station.
Next, we will explain how energy is harvested using the vector dot product. As we know, the dot product of two vectors result in a scalar value representing the magnitude of their projection onto each other. In this case, the energy harvested by a solar panel is proportional to the dot product by two vectors, S and N. S, the sun ray vector representing the direction of sunlight, and the normal vector of the solar panel perpendicular to its surface. The energy harvested can be expressed as harvested energy is proportional to the dot product of S and N. Using the dot product formula, the dot product of S and N equal the magnitude of S times the magnitude of N times the cosine of theta. Here, theta is the angle between S and N. Since both the magnitude S and N and the magnitude of N is also 1 because they are unit vector. This means the energy harvested is directly proportional to the cosine of the angle between sun ray and the panel surface. Energy is proportional to the cosine of the angle theta.
I will go through the calculation of solar panel energy harvesting based on vector analysis. The goal is to determine how the orientation of a solar panel affects the energy it receives from sunlight. By adjusting this angle, we can optimize the amount of sunlight the panel receives. Now let's define the sun ray vector. This vector represents the direction from which sunlight is coming. Using trigonometric functions, we can express the components of S vector. So S vector is given with the column metric with 3 rows. So the first row is cos of 45 degrees times with sine of 180 degrees. The second row is cos 45 degrees times with cos 180 degrees. And the third row is sine of 45 degrees. Simplifies that. So the values is 0, negative 0.707 and 0.707. So this means that the sunlight is coming from an elevation of 45 degrees and a direction of 180 degrees. The normal vector denoted as n vector is given by the column matrix with 3 rows. The first row is sine of 45 degrees times with 180 degrees. The second row is sine of 45 degrees times with cos of 180 degrees. The third row is cos of 45 degrees. Simplifies that, it will get 0, negative 0.707 and also 0.707. As you can see, the normal vector is the same as the sun ray vector, meaning the panel is perfectly aligned with the sunlight. To determine how much energy is received, we calculate the dot product between the sun ray vector and also the panel normal vector. To calculate the dot product means S vector times with N vector. 0 times 0 plus negative 0.707 times with negative 0.707 plus 0.707 times with 0.707 equal to 1. Since the result is 1, this confirms that the two vectors are perfectly aligned, meaning the solar panel is at the optimal angle for maximum energy absorption. So for energy harvested, it is proportional with cos theta.
I'm going to present the next part of the design of the solar panel, which is the angle of the incidence. So the angle of the incidence is the angle between the two vectors, which is in our design, the sun rays vector and the normal vector of the plane. So from the previous slide, we know that cos theta is proportional to the energy harvested. So we get the dot product from the sun rays vector and the normal vector of the plane, which is 1. So we can calculate the theta of the incidence, which is in our case, in our design, the theta should be 0. So to maximize the energy absorption by the solar panel, the solar sun rays vector and the normal vector of the plane should be aligned, should be the same, meaning that it is in the same direction so that the solar panel can absorb the most energy, the maximum energy from the solar panel. So theta should be as close to 0. So in our case, theta is 0. So S vector and N vector should be aligned. So from that calculation, we know that the sun rays vector and the normal vector of the plane, depending on the angle of the sun elevation, the azimuth angle, the solar tilt panel angle, and the azimuth angle of the solar panel. So we need to consider this angle in our design. From the calculation, above calculation and the previous calculation of the vector, we can conclude that the sun rays elevation angle and the solar tilt panel angle should be the same to optimize the energy absorption. So in our case, we choose the angle should be 45 degrees and the solar tilt rotation panel angle should be 45 degrees and the azimuth angle also should be the same, which is in our case 180 degrees. So that is the angle that we need to consider to put in our design. So the next slide is, after we getting those angle, we know that the vector itself, because the vector is depending on those angle. So after we get that, we get the normal vector of the plane, which is 0, negative 0.07 and 0.07, which is, if I representing it into the vector, 0i, negative 0.07j and 0.07k. So after we get those angle, we got the vector, we need to consider where to put the solar panel. So in our case, we need to calculate the gradient of the terrain or the gradient of the place on where we need to put the solar panel. So we get the normal vector of the solar panel, so we need to calculate the vector that is perpendicular to the normal vector, which is the gradient vector of the place. So after we get the vector, that is where we need to put our solar panel. So in our design, we get the vector of the end, so we need to use the cross product, because the properties of the cross product, if we cross product two vectors, we get the perpendicular vector of that vector. So we choose a non-parallel vector. So in this case, we assume that vector is u, which is 1i, 0j and 0k. We cross product that vector to the n vector, which is, if you can see in the slides, so the terrain vector, we assume it to be w vector. So w equals to vector of u, cross product vector of n, and then we can get the gradient vector of the terrain, which is 0.5i, negative 0.07j and negative 0.07k. So that is where we need to put our solar panel, so that we can absorb, or the solar panel can absorb, the maximum energy from the solar panel.
In conclusion, first, solar panel is green, which is eco-friendly. But fixed solar panel cannot absorb the maximum solar energy as much as possible, as efficiently as we want it, because our sun varies depending on location and also time. Therefore, rotating solar panel is a very good option here. It will not only help us enhancing the solar energy harvesting, but also optimizing the absorption. Number 2, in addition, we can determine the optimal angle of the solar panel and also the gradient of installation site by using vector application such as dot product and also cross product. By applying these two principles, we can harvest the maximum solar energy more efficiently. It looks like our presentation has come to the end. With that, we would like to thank you all for your time and also attention. We really hope that our presentation gives as much as input as we wanted to you guys. Once again, thank you very much. Assalamualaikum and have a very great day.